Hi everyone, welcome back. In this lecture, we are going to cover part 2 of Verilog STL design and simulation of UART communication protocol. So this is a complete UART controller project where it can be used either as a UART TX only controller or as a UART RX only controller or as both UART RX and TX controller by making use of some defines. So this is our module UART controller, and here we have few parameters where the clock rate is nothing but our system clock rate, and then we have the baud rate. So at what baud rate we can we basically want to our UART transmitter and receiver to operate. So this is also configurable, and then we have RX oversample for the receiver UART receiver. So the clock and reset underscore n are to our global signals, and then if this controller is going to be as a UART TX only controller, then we have this interface where this is our TX ready signal, and then the data byte we want to transmit, and once we start transmitting, our TX active signal will go high, and then we want the TX data. This is the TX data, serial data which are going to be transferred, and then we have the TX done signal once the data is transmitted. If you want this controller to work as a UART RX only controller, this is our interface where we have the input RX data, and then once all the data is received, for example all 8-bit data is received, we have the RX done signal going high for 1 clock cycle, and we are also basically giving output the data, the serial data received in form of parallel 8-bit data. And if the controller is working as both UART TX and RX, this is our interface where we have the TX byte which we want to send, then the TX ready signal, and once the receiver has received the data, the RX done signal will go high and the data byte, the received data byte. And here are the few internal wire signals. When we have the RX clock tick signal, then the TX clock tick signal, these are nothing but basically the baud rate of UART transmitter and receiver, and then this is the wire signal between transmitter and receiver. So this will get connected basically, for example, UART TX to the second UART RX. Okay, so if so this is how this signal will be used here. If the UART TX, if the controller is working as a UART TX only, the TX data, which is nothing but the output data from the transmitter, will be nothing but this data. And if the UART controller is just a RX controller, this data will get the RX data value. You can understand it in more details by looking at the signals, how they are connected. Now this is our first module, which is basically common for whether this controller is going to work as a UART TX controller or RX controller or both as RX or TX. So this is the baud rate generator module we have here. Let's go a little bit deep into this. So here we have the baud rate generator where we have the system clock, then the baud rate at which we want the UART to be operate, and then we have the RX oversample value, and this is the interface here. This is the RX baud rate and basically TX baud rate, and here we have to basically calculate few variables to basically which will help us to generate the baud rate. So one is TX count. So here we have to generate the TX count based on the system clock and the baud rate at which we want to our controller to work. So this is the TX count, and here we have the RX count, and this is basically to get the width of the TX count and RX count. So for example, if TX count, the value of TX count is 8, then the C log to TX count will be nothing but 3. So based on this width, we have two counters, TX counter and RX counter. So now this TX counter and RX counter, so basically if you understand, this is the concept is similar to a frequency divider concept, where by making use of the counter we are dividing some frequency. So basically here the system clock is 25 megahertz, and we want to generate a frequency which is baud rate 115200. So basically we have to divide this. So this all things we are doing to generate the baud rate. So based on the clock rate and baud rate, we will first calculate few TX count and RX count parameters, and then we will have two counters which will. So if you see here on reset, while generating the RX baud rate on reset, we are initializing these two registers to 0, and once the RX counter is, so this procedure is basically running at positive edge of the clock. So at every clock edge we are basically incrementing our counter. So once the counter reaches to RX count -1, we are basically toggling the RX clock tick, which is nothing but the UART receiver baud rate. So this is how we are generating the baud rate. This is very simple concept. Hope you will understand this easily. If you have any doubts related to it, you can write down in the comment section and I will explain it in more details. Now let's understand further. So if we are this controller, we are using it as a UART-TX only, then we have to instantiate this UART-TX controller, and if we are using it as a UART-RX only, we have to instantiate this UART-RX controller. Else, if we want to make use of this controller both as UART-RX controller and TX controller, we are going to instantiate these both UART-TX and UART-RX controller. So now let's understand the UART-TX controller. So as I explained, the interface signals, these are the interface signals, and then we have the state. So I have covered the state diagram and the block diagram of UART-TX controller and RX controller in part 1 of the of this lecture series. So if you have not gone through that, I would recommend you to first go through that, so you will understand the state diagram and the transition table of the UART-TX controller as well as the RX controller. So here we have in few internal variables. Bit index, which basically keep tracks of the bits, transferred bits, and then TX done, TX data. This is the state transition variable, and we have the TX active register signal. So on reset, we are initializing all these to zeros, and once we are in idle state, these are again the value of bit index, TX done, TX data will be 0. And once we are in idle state, and if the TX ready signal, if the input TX ready signal is high, we will basically go to the TX start condition. And once we start, we go to start state, our TX active will become high. Basically the meaning is our transmitter is in active state. Else we will remain in the idle state. So in start state, we are basically pulling our TX data line to low, and we are going into the data state, where in the data state we are basically transmitting the data. Okay, so the TX data will get the ITX byte, which is input parallel 8-bit data. So bit by bit it will be assigned to TX data, and along with that we will keep calculating, or we will keep tracking the bits by using this bit index. So if the bit index reaches 7, that means we have transmitted all the 8 bits of data. We will what we will do, if we are less than 7, then we have not transferred all the data. So we will be incrementing the bit index, and we are going to be remain in the UART-TX data state only. But once we have transferred all the 8-bit data, our bit index will become 0, and we will go to the stop. We will go into the stop condition, where in the stop condition we will basically, the TX data will we will making it high again, and the TX then will become high, the TX active will become 0 here, and we will go into the idle state. Default UART-TX will be in the UART, the state will be UART-TX idle. So this is where we have the output. So the output TX done will be nothing but this input TX done value. The output TX data will be input TX, the registered TX data, and the TX active will be registered TX active. So I hope the concept of UART-TX controller is clear to you. Now let's go to the UART-RX controller. So here we have the RX controller. As I explained, these are the interface signals, and then we have these states defined, and again these are the some variables which are similar to the UART-TX controller. So here we have another extra internal register variable, which is clock count. So here you can see, so here you know that the UART-RX controller will be running at the UART-RX baud rate. So basically at that baud rate it is working, and now depending on the RX oversample, basically we have to fulfill the RX oversampling mechanism. So I have covered the detailed RX the oversampling mechanism in the part 1. You can go through that if you have not gone through that yet, so that you will understand the oversampling concept in more details. So this the clock count is basically, here we are going to keep track of that oversampling counts. Okay, now on reset, again we are initializing these registers, and in idle state again we have these bit these register value zeros, and in the when we are in idle state and when our RX data, RX input line is 0, that means the transmitter has started the start bit. So if the RX data is 0, that means the start condition has been detected and we will go into the RX start state. Otherwise we will be in the RX idle state only. So once we are in the UART RX start state, we will basically in the start state we are basically going to sample the start bit at the middle. Okay, for that we are going to check the RX oversample by 2. For example, we are sampling the data at oversample 16 times oversampling value. So that means there will be 16 pulses corresponding to one transmitter bit. So to sample that data in the middle, we have to basically, when this clock count reaches to half of that RX oversample value, we will check if the RX data is still 0. If the RX data is still 0, that means this is the input start bit and we will go into the RX data. Otherwise we will be in the RX idle state only. So I hope this is clear. So I have covered this concept of oversampling in the part 1, so you will understand. So once you go through that part, you will understand this piece of code in more details. So once we are in RX data state, again here we are sampling the data bits at middle of it, and that value will be we are going to keep in our this RX data register. Okay, so once the RX clock count, when the RX clock count is less than RX oversample value, we are in the RX data state only, and our counter will keep on increasing. Once RX clock count reaches to RX oversample value, we will get that value and we will put that value in our RX data internal register variable, and we will clear the counter. Now if we have received all the bits, that means if our bit index is less than 7, that means we have not received. So until then we will be in the RX data state only. Otherwise we will go into the RX stop state. In RX stop state, again we are going to sample the stop bit. So again the same by making use of the same oversampling mechanism, we are going to sample the bits in the middle of it, and after that we are going basically to the idle state, and our counter will be cleared and our RX then will be high, and we will be in the idle state, and default also we will be in the idle state, and the RX internal signal register value will be assigned to the output RX done. And once RX is done, then the RX data will be put at the output port, which is ORX byte. So I hope this piece of code is very much clear to you. If you are little bit confused about this oversampling and how we are making use of this oversampling here and basically detecting the input bits, it will be more clear if you first go through the part 1 where I have covered the oversampling concept in more details. Still, if you have any doubts, you can write in the comment section and I can explain you in more details. Okay, now let's understand. So I hope this is clear. Now let's understand the test bench part of this Verilog project. So here this is the test bench. So again these are the few parameters. These will basically defines what is the clock period. So we have taken the 40 nanosecond clock period, that means which is 25 megahertz clock frequency. So the clocks per bit will be 217 and the clock bit period is equal to 8680 with respect to 115200 baud rate. Okay, now here we have our signals. So this is the clock reset signal. If it is UART only, then we have these signals, and if it is UART RX only, we have these signals, else we have these signals. So if it is UART only, basically our interface will be different. So we have to take this interface and we have to make the connectivity accordingly. For example, if we have the UART only interface, then these are our signals. So we have to use these signals. If UART RX only, we have to use these. If UART and RX both are there, we have to use these interface. So this is how we will instantiate the DUT. Now here we are generating a clock signal of 25 megahertz, and if it is UART only controller, this is how you can basically transmit it. You can test it. So here I am sending the data here. after I'm asserting the reset, deasserting the reset, and then after 2 clock cycles the TX ready is going to be high, and then at the positive edge of the clock I am sending this data. So this data you can check it through the waveforms. Now when we are using it as a UART RX only controller, then basically when our project is as a UART RX only controller, then our test bench will be like UART TX controller. So the test bench is going to work as a UART TX controller. So we are going to send some data. So here at every positive edge of the clock we are going to send some data. So that data, the receiver, the test bench which is going, the design which is going to work as a UART RX controller will receive the data, and that data you can visualize in the waveforms, and also by putting some print statements as well. Now this is how we are going to test it here properly. So when our project is going to work as a both UART TX controller and as a RX controller, then here we are going to first send some data, and then we are going to receive some data, and then we are going to check if both data are equal. So if you see here at positive edge of the clock, first we are making sure that our TX is ready. So once our TX is ready, that means our transmitter is ready to send the data. So then we are sending this data TX byte. Okay, so we are sending the TX data byte. Then so here if you see, this for loop will start here and it will end here. So here the first byte is sent. So the first byte is sent, so the UART transmitter will send the first byte, and the receiver will receive it. So when receiver will receive the byte, it will, the RX done signal will go high. So on positive edge of the RX done signal we will get that received data. So that received byte data is nothing but RX byte, which is present at the output of RX controller. So if the data sent and the received byte is same, then our test has passed. So likewise this for loop is going to send some 8 bytes of data. So we will send the data byte one by one, and we will check if that has received properly at the receiver side. Okay, now I am going to simulate it and going to see if the data is transmitted properly through the RTL and through the UART communication protocol. So here I have selected the Aldec Riviera Pro simulation tool, and I will take this open epwave after run. We will save this and we'll run it. So if you see here, we are sending the data to send. So data to send is nothing but these values. So we are going to send these values, and if you see here, we will sending these byte one by one, and then we are receiving. Once RX done is high, we are receiving this byte and we are comparing both. And if both are equal, then the test has passed, otherwise the test has failed. So if you see here in logs, you will see that test has passed. So the first byte is 01. So if you see here, the first byte is 01, the second is 10, the third is 22, then 32, 55, AA, AB, and 88. So we have received all the bytes. Now let's see in waveforms. So this is the waveform window. Actually it has opened it here. Let me zoom in little bit. So we will make sure that our TX ready is high. Once TX ready is high, we will send the byte, and this byte the transmitter will receive this parallel data, and it will transmit serially to the RX to the UART receiver, and then UART receiver will receive the data. So in the UART receiver, once RX done is high, we will see what is the data it has received. So if I may go to right side, so here the RX done has it went high here. So once it went high, then what is the data? The data is 1. So what is the transmitted data? TX byte is 1 and it has received 1. That is correct. Now let's see the next byte. And if you see another thing here, once the RX done is high, we are sending the second byte. So the TX byte here is 10. Now this 10, once it get received by the receiver, the RX done will again go high. So if you go and left side and see, it has again go high, and once it went high, then what is the RX byte? RX byte is 10. So this byte will receive here. Now once RX done is high, we will send the next byte, which is 222, and it will be received at the next RX done when it went high, when it goes high. So I hope this UART communication protocol, Verilog SDL design and test bench coding is very much clear to you. If you have any doubts, please write down in the comment section. Also, if you like this video, please consider subscribing this channel and press the bell icon so that you would get notified as soon as I upload a next lecture video. Thank you very much.